look at a range of chemical features around an intriguing reaction, that of aluminum with iodine. I'm going to start with a process called See, Think, Wonder, and it's part of Project Zero, Making Thinking Visible, and a routine for investigating interesting phenomena. So questions that you're going to ask: what do you see? What do you think about what you're seeing? And what does it make you wonder? And we're going to start by looking at the separate elements and what's going to happen when they react. Make a prediction and try to support the predictions of your observations with reasons and ideas. And don't just stop at a single idea. What does it make you wonder? What questions does it generate in a larger theatre of ideas? And you can think of these ideas following on from each other to begin with. Think of each individually to be able to think deeply enough. I'm going to start off with the reaction. Pause this to reread things very thoroughly. Important to start off with safety, and you're going to use a fume hood, safety goggles, and the students around will wear them as well. Don't mix the chemicals until you're about to perform the experiment, and have a paper towel under the iodine container. It just stains. It's a disinfectant. And any apparatus, the spatula you used, keep on the paper towel. The materials, picture of some aluminum to the left. You'll finally divide the iodine and grind it, pestle in a mortar, and a few drops of warm water. List here of the equipment to do the reaction on a watch glass is ideal, and the other items that you need. Again, keep pausing to do this. As importantly is the cleanup. Make sure all of the materials have reacted, and while it's still in the fume hood, and the fume hood's turned on, add a little more water to make sure the reaction goes to completion. Allow it to cool, dispose of as solid waste, and the iodine that was crushed in the pestle and mortar, just put a small amount of pretty dilute potassium iodide solution and leave it to soak for a few minutes, and it cleans up very, very quickly. And here's the procedure. And remember, don't mix until you're actually going to do the experiment. So when you are sort of a minute or so just before you're going to add the water, mix them together and stir well with a glass rod. To the mound, make a small dip in the top, and you can add a couple of drops of water to it. So what do you see? What are you thinking? What questions arise? That is our see, think, wonder. And then the reaction itself is one of the best review sections that you can do. It covers so many topics. And so look at the ones here. It really does cover all of these items. So we've got the elements on the periodic table. Why are aluminum and iodine elements? They're made up of one kind of atom, and they're on the periodic table, and only elements feature on the periodic table. And the other possibilities would be mixtures and compounds. Describe the compound that's formed. And then going back to the periodic table, where do they appear? Aluminum is a couple of rows higher and to the left of iodine. And what does the position tell you about the two elements? And if we put in the zigzag line, the boundary between metals and non-metals, aluminum is a metal, iodine is a non-metal. Though when you look at iodine, it sort of looks a little metallic before you grind it up more. Here are the electron arrangements. Aluminum, group 13, 3 electrons in the valence shell. Iodine, group 17, with 7 electrons in the valence shell. And the electron configuration with the subshells, again, confirming 3 for aluminum, 3s2, 3p1, and 7 for iodine, 5s2, 5p5. And we can write the formula for the product. We've started with 2 elements in the compound, potassium chloride and a couple of others, and aluminum iodide is also a binary compound. And we can look at this structure here is the first element a metal, and you can follow your way down, read through it, pause this to see how you're going to get the formula. So if it's a metal with non-metal, we go on to the second part, it's going to be ionic. We'll come back to bonding in a short while as well. And this is how you look at the charge on the ion and join them together so that the compound has no overall charge. And for equation practice, you're going to use the formula for aluminum iodide, which is the product, and the reactants of aluminum and iodine. So start with the word equation, so you know exactly what you're doing, and then write the symbols and formula for both. Remember, iodine is diatomic. Using Hinkelbroth reminds you of that. And then you're going to look at the valency combining powers to get the formula. Aluminum is a 3+ ion, iodine is a single negative, so you need 3 iodide ions to every 1 aluminum. And then you're going to balance to end up with the same number of each type of atom on either side. You can't make something, you can't lose it. And so if you look at iodine, the coefficient in red in front multiplied by the subscript after the iodine means you've got 6 iodine atoms. So you need 6 on the left-hand side in the reactant, so 3 iodine diatomic molecules. And the aluminum in the product, it's 2 Al. And so you've got the 2 to balance on the other side. And you can do an audit, adding up each of them to confirm it. And reacting chemicals, a broad term here. Is it an exothermic, endothermic reaction? Does the reaction occur spontaneously? Is there a high activation energy? What's the limiting reagent? And here you can see fumes of iodine that are being given off basically by the heat of the reaction as well. What types of reaction do we have? These are the possible ones: synthesis, decomposition, single replacement, double replacement, and redox, which is including combustion. And we've got aluminum plus iodine, 2 reagents, 2 elements forming a compound. So it's going to be the synthesis at the first of that list. And also called combination. And types of reaction here with forming a single compound. And then looking again at a type of reaction, so it's still synthesis, but it's redox, oxidation reduction reactions, and addition of oxygen, removal of hydrogen, removal of electrons, increase in oxidation number. So you're looking at one of the reactants and seeing if this list applies to it or applies separately to the second one. Whenever you have oxidation, you also have reduction. So if it is a redox reaction, one of the chemicals will be oxidized, one will be reduced. It doesn't have to add oxygen. There might not be oxygen in the reaction. There isn't in this one. There's air around it, but it's not actually taking part in the reaction. And when we're looking at the reaction of aluminum with iodine, let's have a look at aluminum becoming an aluminum ion in aluminum iodide, and with the removal of 3 electrons. In the case of the addition of electrons, iodine gains 1 electron, that's filling the valence shell, to become a single negative charge. And we'll see more about that as we look at bonding and the structure of the materials. And again, reminding you that you've got a metal and a non-metal, so what type of bonding is occurring? That's going to be ionic bonding. And you're going to use the valence electrons to describe what happens. Again, looking at the periodic table, aluminum has 3 valence electrons and iodine has 7. And we can draw the Lewis structures. These are of the atoms before bonding. And I haven't shown the diatomic iodine, I'm just showing a single I here. And what actually happens, a single electron from the aluminum goes to 1 iodide atom, and you form an iodide ion. So each of those 3 aluminum valence electrons are given to 3 separate iodine ions to become 3 separate iodide ions, and you have to show the charges on each of the species. And so if you're really looking at the Lewis diagram, that's how it would end up. Aluminum, the metal, has given up its valence electrons, so you don't show any electrons, it's given them up. The iodine has gained it, actually 3 iodine atoms gain 3. You can also look at it in terms of or the Bohr structure, again with the valence electrons, the 3 aluminums filling the valence shell, the 5p shell of the iodine atom. And so once they've been transferred, you've now formed ions, and the electron configuration of aluminum is now 2,8, so it has the noble gas electron configuration, the same as neon, but it's aluminum because its nucleus is the same, and ditto with iodine getting a full outer shell. And remember, there's electrostatic attraction between them. An IB for bonding is requiring you to say you've got both a cation and anion in an ionic bond, which are held together by electrostatic attraction. Ionic compounds are usually crystalline solids, finely ground into powders. They usually have high melting points, and the ions are arranged in an extended lattice because of the attraction between oppositely charged ions. And here's the product, a picture of the product here. Ionic compounds don't conduct electricity in the solid state. The ions can't move in the solid state. They do when they're melted, because the ions can move. They do in aqueous solution. They usually dissolve in polar solvents, for example, water, and their melting points are usually high. And whilst we're looking at a reaction, just let's go through observations. So a little bit of see, think, wonder, but more formally, if you're writing observations in a results data section of a lab, give the qualitative ones as well as any measurements, quantitative ones, and say to yourself, I need to describe the appearance before for each reactant, the appearance during, sometimes it doesn't change, the appearance after the reaction, and other qualitative descriptions, sparks, flashes, sounds, odor, and anything else that describes that. And of course, go back to see, think, wonder. So thank you, Ms. H, for your lab work and the use of laboratory facilities at Washington International School. Much appreciated.